viscous force.
Okay. Now, what you said for the geostrophic flow, what is the condition?
That
Almost
almost this
zero.
this should be 0, then only it will come into effect.
And so, what
And
is
also
happening there? Which are the terms going away?
this,
Hmm.
this, and
Hmm.
this.
So, what you left with there?
Then left to it only this Coriolis storm and the pressure gradient. These two are mainly important.
Yeah. So, you have to solve that.
Yes.
Okay. Okay then. Yeah.
Thank you.
Good.
I am from Equi Foundation for Higher Education, Hyderabad. I am under the supervision of Dr. Gautam Kumar, and my area of research is fluid flow through porous media. And today I am going to discuss about the task number 2.4.2, which was given by Professor Starchenko, sir. As of now, Kangana was derived the momentum equation to the planetary convection, planetary motion. Now the task is the task number 2.4.2. is that carry out the detailed transformations to obtain the system of three scalar equations 2.9 from the first equation, from the first vector equation of the geostrophic system 2.8, where 2.8 is given by two v cross del z minus del p is equal to 0, where this del g is the unit vector in z direction, and this is the pressure gradient, and this is the vector, and this whole term represents the Coriolis force, and this term represents the gradient of the pressure. And we have to show that 2.9, which is given by del p by del z equal to 0, and v phi is equal to 1 by 2 del p by del s, and vs equal to minus 1 by 2s del p by del phi. Okay, to prove this 2.9, we are going to use the cylindrical coordinate systems to the geostrophic momentum equation. So we convert from x, y, z to s, phi, z, where s is the radial system, radial component, p is the azimuthal component, z is the vertical component. So the vector v is given by, from in cylindrical coordinate, vs, v phi, vz, and the gradient p is given by del p by del s, comma 1 by s del p by del phi, comma del p by del z. Okay, let's rewrite this system 2.8. 2v cross del z equal to del p, and where this vector del z is 0, 0, 1, not vector, this is the unit vector. Okay, so let's calculate this 2v cross del z. Which is given by, okay, del s, del phi, del z, and v is the vs, v phi, vz, where del z is the 0, 0, 1, where del s, del phi, del z are the unit vectors in cylindrical coordinate system. Let's calculate del s times v phi minus del phi times, okay, vs plus del z times 0. So we are remaining with v phi. Okay, this is 2 multiplied by 2 2v pi 2vs minus 2vs comma 0. So let's compare this equation 2.8 with this del p and 2v cross del z. Will get del p by del s is equal to 2v phi. From here we'll get v phi is equal to 1 by 2 del p by del s. Similarly 1 by s del phi by del s is equal to minus 2s. From here we will get vs equal to minus 1 by 2s del phi by del s, and another one is del p by del z is equal to 0, and these are the required system we have to show. Okay, and thank you. Cylindrical coordinate system, sir, we have used.
Yeah, but some coordinates are entered in the description of just what it depends on them. But there is one coordinate which is independent.
Z, sir. Z is independent.
Yeah. So remaining.
Remaining are independent. Dependent.
Yeah, just
S is dependent on S and phi.
yeah, it's the main dependent.
Yeah. Yeah, sir. Radial and azimuthal are dependent. Thank you, sir.
Kamlesh Sage, I'm from Chennai. My institute is SRM IST in Katagama campus. My research topic is FSI and in blood flow in using the arterial. My area is fluid dynamics. I taking the today topics finite volume methods. So I go for 2-dimension study diffuse equations for discretization. And 2-dimension dou by dou x of lambda dou phi by dou x plus dou by dou y lambda dou phi dou phi by dou y plus source term equal to 0. Now first and take a grip point and knobs. This center point is P, and this east directions and west directions. Y directions are north direction and south directions. N2 E is the direction is we taken del x del y n, E to S del y s, and these total directions del y west to s is del x w, south to east del x e, and this total direction del x. And first equation we integrated in over the control volume, integrated del v dou by dou x lambda dou phi by dou x del x del y plus integration over the del v dou by dou y lambda dou phi by dou y del x del y plus integrations s phi del x and del y equal to 0. Now integrate that, we get finally lambda e lambda dou phi by dou x into del y from e minus del to dou phi by del x from del y from w plus lambda dou phi by dou y del x from north minus phi dou phi by dou y del x from south, and we write source term as capital phi into del v equal to 0, and we substitute in the limits and we write the Fick's phase terms dou phi by dou x to e, we write phi e minus phi p divided by del x e dou phi by dou x from w, we write phi p minus phi e phi w dou x w dou phi by dou y n phi n minus phi p del y n dou phi by dou y to s phi p minus phi s divided by del y s, and we substitute the third equations and also the substitute the lambda e by del x e phi e minus phi p minus lambda e aw del x e del x w phi p minus phi w lambda n a n by del y n phi n minus phi p plus lambda s as del y s phi p minus phi s, and we so term write the for linear model sc plus sp phi p. Now all term we rearrange the phi p ae plus aw an as I give the value for ae equal to lambda e ae del x e aw equal to lambda w aw del x w, and an equal to a lambda n an del. Okay ma'am. As equal to lambda s as del y s, and ap right ae ae plus aw an and as, and so term sp del x and del y, and we are in ap phi p equal to ae phi e plus aw phi w plus an phi n as phi s plus so. And this is get the result for descriptions 2 dimensions over. Yes. Ma'am, here using the Gauss divergence theorem to volume to surface, and then we integrate the normal wave for the to surface. Gauss divergence theorem requirement to the volume convert the volume to surface area, surface integrated.
Okay. Could you estimate somehow the accuracy of your scheme?
Scheme.
What is the accuracy of this scheme? Okay, can you estimate it somehow? Or error, otherwise error. Can you estimate the error via this some, I don't know, deltas or whatever? Second order, yeah? So in terms of this delta, yeah?
Second order.
Second order.
Okay.
Okay, okay. So you have to work for the boundary nodes also.
Yes, ma'am.
Okay, you know na boundary nodes.
Yes, ma'am.
Yeah, near the boundary it is half of the grid size.
So after the unit size, the del x by by 2, ma'am.
Del x by 2 also will come. Del y by 2 also will come. Because you have dealt with the two-dimensional case. Yeah. So, okay. That also you have to write down separately. This is for the internal nodes.
Internal also.
Okay, okay. Have you tried any problem?
No, ma'am. Now only started this topic also, finite volume method.
Where you want to use it? For your
In my research, ma'am.
in
my
your
work,
research work. Oh, very good. So you understood.
Yes, ma'am.
Good, good. Okay. Good.
Thank you, ma'am.
Good afternoon, everyone. My name is Anup Suresh. I'm from Bangalore. I'm doing my PhD in Vellore Institute of Technology in Vellore. And the topic of my research problem in PhD is the study of the investigation of chaos in nonlinear dynamical systems, particularly in magnetoconvection and rotating convective systems. So the topic I've chosen for my presentation is Introduction to Weakly Nonlinear Analysis through Regular Perturbation Methods. So firstly, let me comment on what we mean by weakly nonlinear. So basically, when we say weakly nonlinear, we're referring to a small nonlinearity that arises in equations. So basically, terms with or equations with nonlinear terms which are small in magnitude. So so when we have such equations, we can treat the nonlinearity as a perturbation to the linearized problem, as in we can treat the nonlinearity as a correction to the linearized solution to the problem. And doing so allows us to pursue different sorts of perturbation techniques for us to solve the problem. So in general, any kind of weakly nonlinear system can be expressed as a general form as Lu plus epsilon n of u equal to 0, where epsilon is a very small parameter. Weakly nonlinear problem. Lu here is the linearized problem. So Lu equal to 0 gives the linearized problem, where L here is the is any kind of operator, a linear operator. U is a dependent variable. Epsilon is the perturbation parameter, and n of u is the nonlinear term in u. So basically any kind of nonlinear term in u. So here the condition for us to use a perturbative expansion is when epsilon is very much less than 1. That is, epsilon is a very small parameter. So for such a system or such an equation, the general solution can be expressed as u equals u naught plus epsilon u1 plus epsilon square u2 and so on. So basically the solution can be expressed as a series, a perturbative series, and this is only for what we call as regular perturbation. So again, there are two types of perturbation. Coming to the types of perturbation, we have regular perturbation, techniques, and we have what are known as singular perturbation techniques. So now what are the main differences between regular perturbation techniques and singular perturbation techniques? Now in regular perturbation techniques, the solution here, so this is the solution, varies smoothly with epsilon, where epsilon is a perturbation parameter. Examples, I'll just write it here. R stands for regular and S stands for singular. So yeah, so example for a regular perturbation problem is, let's say x minus epsilon x square equal to 1. So epsilon here is the perturbation parameter. For singular, it's epsilon, let's say y double dash plus y prime plus y equal to 0. Now, if you can see here in singular perturbation problem, epsilon occurs as a coefficient of the second order of y, differential coefficient of y. So, so in such a problem, in such a singular perturbation problem, so the solution exhibits a rapid variation in some regions, some domains of epsilon, and does not vary smoothly with epsilon. In contrast, regular perturbation techniques, the solution has to vary smoothly with epsilon, and which comes to my second point, which is that in regular perturbation techniques, as epsilon reduces to 0, that is, as epsilon tends to 0, we arrive at the linear case. So in this case, when epsilon is equal to 0, we get u equals u naught, which is the solution to the linearized problem LU equals 0. And you can just see here, when epsilon equal to 0, we get x equals 1, which is the linear solution. And the perturbation when epsilon is small is about the linear. So epsilon something plus epsilon square something and so on. Whereas you don't have that case in the case of nonlinear, I mean, a singular perturbation technique, because when you equate epsilon equal to 0, what you arrive is not the second order differential equation, but the first order differential equation, which is different. The nature of the solution itself is different when you compare to the second order. So, so in regular perturbation techniques, the solution converges uniformly to the linear solution when epsilon tends to 0. Whereas in a singular perturbation problem, it may or may not converge uniformly to linear solution as epsilon tends to 0. And so in regular perturbation problem, the solution can be expressed as a Taylor series, as in any sort of series, whether it's Taylor or Maclaurin. Whereas in singular perturbation problem, it cannot be expressed in the form of a Taylor series, at least not in all domains of the problem. So those are the differences between regular and singular. So now coming to my main topic, which is basically here we are only dealing with regular, because in singular it's still a hot topic of research and not very many things are known about singular perturbation techniques. Whereas regular, we know quite well about regular perturbation techniques. So let me give a simple example to begin with. So we take the same example, x minus epsilon x square equal to 1. I'll rewrite this in a familiar form, which is x minus 1 equals epsilon square. So as you can see, this is linear, whereas non-linear term occurs in the right hand side. And setting epsilon equal to 0, as I said, gives you x is equal to 1, which is the solution to the linear problem. So let's express the solution for the nonlinear case, for the equation, in terms of series expansion. So I take x naught plus epsilon x1 plus epsilon square x2 and so on. So we already know that x naught equals 1, but we'll show that we obtained the linear case at the first order of epsilon. And to do this, we just substitute the expansion in the main equation. So we have x naught plus epsilon x1 epsilon square x2 and so on, minus epsilon x square now. So I take the same equation, and I've rewritten it, so it's like, so now now we rearrange in such a way that we obtain different orders of magnitudes for epsilon. And so we have, just comparing, we have x naught plus epsilon x1 plus epsilon square x2, and so on. minus 1 equals epsilon. We have, let me just consider the first two terms and neglect the others. So we have x naught square, a plus b the whole square is epsilon square plus x naught square plus epsilon square x1 square. Then we have plus 2 x naught or 2 epsilon x naught x1, and this goes on. So now I gather the terms which are coefficients of epsilon at each order, and what I get is at the first order, that is at epsilon to the power of 0, the leading, what we call as the leading order, we get this. So this is nothing but at the first order. So that is what I get is I get x naught minus 1 equals, there's no term of the leading order here, so 0, which is basically what we get as a solution to the linearized problem. So that this is basically what it means is we're just setting epsilon equal to 0, and what we get is the linear problem. Now, so this is basically the trivial case. Now, gathering the terms at the first order of epsilon, we get, so we have this term here, epsilon x1, so x1, and we have epsilon x naught square, so it's x naught square. So we already know the value of x naught, which is 1, so at the value of x1 is 1 again. Now we look for terms which are at the second order of epsilon, and so here we have epsilon x2.
Anup?
Yeah, so gathering the terms at the second order of epsilon, we get x2 here, so equals epsilon x naught square, which is yeah, so yeah, this term here, epsilon times epsilon, so you have 2 x naught x1. So we know the values of x naught and x1. X naught is 1 and x1 is 1, so we get x2 equals 2. And similarly for epsilon cube, we have x3, which is here. x3 equals, we have x1 square plus yeah 2 x naught x2. So here there's an additional term here, so it's 2, we have 2 x naught x2. So that is, so x3 is, x1 is 1 plus 2, x naught is 1 and x2 is 2, so 5, right? So, and so this we can go on epsilon to the power of 4, 5 and so on, but we just since we've obtained 4 terms, we're in a position to write the series. So the solution is this x naught is 1 and epsilon x1 is again 1, x2 is 2, so we have 2 epsilon square plus x3 is phi, so phi epsilon cube and so on. So basically epsilon, this term here is the correction to the leading order, 2 epsilon square is the correction to the first order and so on. So we managed to obtain a solution as a series expansion in epsilon for the value of x. And again, just checking, epsilon equals 0 reduces our problem to the solution of the linearized case, which is x equals 1. So yeah, this is a simple problem, simple algebraic problem. Next, let us let's study the case of a little more complicated problem, which is a differential equation. And one such differential equation involving regular perturbation scheme is what is known as van der Pol oscillator. And van der Pol oscillator is an example of an oscillator which is non-conservative and has a damping term of the first order. So we have so the equation of the van der Pol oscillator is given by d square u by dt square plus u equals epsilon 1 minus u square du by dt, where epsilon is a very small parameter. Now if you can see, d square u by dt square plus u equal to 0 is the equation of a simple harmonic oscillator, or just a harmonic oscillator. And this term here is the damping term of the first order, which has du by dt, and so it's a damping term. And so such an oscillator is non-conservative, as in it doesn't have a periodic solution. So we have performing similar sort of analysis. We can just obtain the linear case, which is when epsilon equal to 0, we get the usual harmonic oscillator equation, a periodic harmonic oscillator equation, and the solution to such an equation is given by u equals a cos t and phi. So you all know how the solution can be obtained. You have a differential equation of the second order, which is homogeneous, and so there's only complementary function. Just solving this, we get this equation. In general, it can be expressed as both sine and cos, but this phase shift or like phase angle makes up for the sine as well. So we have a cos of t plus phi as a solution. Now, so again, the solution of the original equation, that is a nonlinear equation, can be expressed as a function of t and phi given by u naught of t, which is basically this this term, the linear term, the solution to the linear problem, plus epsilon u1 plus epsilon square u2 and so on. So yeah, let me just call this 1, 2. So now we substitute equation 2, which is a series expansion, in the original equation 1. So we substitute 2 in 1 to get So we get so I'm just substituting and rearranging. So d square u1 by dt square plus u1 plus the coefficient of epsilon square, which is d square u2 by dt square plus u2 and so on. And then we have the right hand side, which is epsilon 1 minus u0 plus u1 plus u square, so 1 minus u square. So we have the square here, and then we have the first order differential, which is u1 by ut plus epsilon square du by dt and so on. So now rearranging the terms, we get d square u0 by dt square equals u0 plus epsilon plus
Anup, you have taken 15 minutes.
yeah.
Yeah. Write the answers now if possible.
I was not
Proceed.
informed that 15 minutes is the limit.
No. It's okay.
Just 5 minutes.
Yeah. This one you can skip. The
Yeah,
middle
so
portion.
basically I'm just substituting
Yeah,
the
that's what I want to
series
say.
this. And so basically I'll just, if you do the substitution, what you get at epsilon naught, you get the same equation to the linearized problem, which is u naught equals a cos of t plus phi, right? And at the first order, so what we get is d square u1 by dt square plus u1 equals 1 minus u0 square du naught by dt, and we just substitute the terms. We already know the formula for u0, which we obtained in the first order, and so it's basically a trigonometric function. So performing, trigonometric manipulations, what you get is just write it here. This is the answer for the first order. So you have u1 equals, we have a cube minus 4a by 4 sine t plus phi plus by 1 by 4 a cube sine t plus phi. This is after performing trigonometric manipulations using identities. And so now, we can obtain the solution for u1. You can treat this as a complementary function, and you have the particular integral, the part given by this. And then we obtain the solution u1, which is, I'll just write the particular solution. General solution just follows from that. So, which is minus a cube by 4a by 8 t cos t plus phi minus 1 by 32 a cube sine 3 t plus phi. So this is for the particular solution. And so now from this you can obtain the formula solution for u1, and now you have u0 and u1. You can do the second order as well, but I'll just stop at the first order, which is to get the general solution as u1 cos of t plus phi, which is the linear solution. Sorry, u equals the solution, and then you have epsilon u1, which is given by this. And if you want, you can carry take it to the further orders as well, epsilon square u2 and so on. So this is how you solve a regular perturbation problem when it comes to a differential equation such as van der Pol oscillator. Yeah. Thank you.
Good.
Topic we just mentioned that this is very much resumes that Rameshwar did in his lecture.
Yeah.
So perhaps we are working together, is it?
No, we're not working together. Yeah, I just chose this topic.
Okay, so one small question is that is this dependence with taking into account first to the correction, is it still periodical or?
No, this is not periodic because it has t here. This is periodic because it has a cube sine 3t plus 5, whereas because of this term, it's not periodic. Which is why it's called as a periodic oscillator. Van der Pol oscillator is an example of a non-periodic oscillator.
But this addition, is this some sort of the trend, or what is that actually?
As in?
Is it some sort of the trend, or maybe it's what form this addition have?
I mean, so basically when we...
So on top of periodic solution, is anything that just trending it away from the, or maybe tends to infinity, I don't know.
Yes. So you consider more and more of these terms, you gather more and more of these terms, you start making the solution more and more non-periodic. As in non-periodicity occurs in each of these terms. And the original at the first order, at the leading order, it is periodic. This is basically when you substitute epsilon equal to 0, you obtain the regular harmonic oscillator, which is a periodic oscillator. But as in when you gather these terms here, epsilon u1, epsilon square, u2, so u3, u4, u4, the solution starts becoming more and more non-periodic.
But all this correction, especially the more higher corrections, they are multiplied it by a small parameter. Maybe this non-periodicity somehow compensates each other. I don't know.
No, because yes, compared to this is a small parameter for sure. But even this depends on the value of epsilon that you are taking. The overall solution is non-periodic. So when you plot the graph of a Van der Pol oscillator, what you can see is a damping term. And if you look at this equation here, when epsilon is not equal to 0, even when it is a very small term, this may not necessarily be a very small term. For instance, the general form of a Van der Pol oscillator doesn't mandatorily require epsilon to be a very small term. We have taken it to be a small term for us to solve it using perturbation analysis. In general, epsilon can be 5, 6.
But is there any physical justification of smallness of epsilon or not?
I mean, when it is small when the damping is small. So when you have a small you have a harmonic oscillator and you have a very small drag coefficient is very small. Let's say air resistance, which is very small, which is, resistance nonetheless. So because of the drag force, it includes a very small parameter, small non-linearity or like non-oscillatory characteristic to the system. So when the drag force is large, epsilon, which means that epsilon is large, you have a totally different solution which we cannot solve using nonlinear analysis because this term becomes very large.
Oh, okay.
So this is applicable only when epsilon is small, and so we have taken. So this is basically as I said, this doesn't require for the general Van der Pol oscillator. This doesn't require a very small term. It may be a very large term as well. But for us to solve using nonlinear analysis and perturbative methods, this has to be small. Only then we can solve using regular perturbation techniques.
Okay, thank you. But maybe my final question is much more severe. You started from the algebraic equation, yeah? And in this algebraic equation, you put the regular perturbation and found that it's working. Yeah. But if you look better on this equation, you see it's just quadratic equation. And it has second solution, which is inversely dependent on epsilon. So so your regular system becomes singular.
Right. So no, that was just so you mean this x minus epsilon, this one? Yeah,
exactly. Yeah. It's actually quadratic equation, and if we consider the second solution of it, you consider only one which is close to 1. But there is a second solution.
Yes.
An order of magnitude of this second solution is roughly inversely proportional to the square from epsilon. So,
Yes, yeah,
so it's become singular.
Yes, yes. This.
So this is sort of interesting problem.
Right. So through I just considered this problem to show the method of regular perturbation. So in general, of course, we don't solve these kind of problems in regular perturbation method. This is just for me to as an introduction to solve the van der Pol oscillator equation.
Okay.
So we don't generally solve such equations in using regular perturbation techniques.
Okay.
So
Thanks.
this was just an example, like a prelude for me to.
But now this is an interesting problem.
Yes.
Which start to be regular, then it's become singular.
Okay, I want to know, is there any restrictions on this method? When we have to apply, when we should not use this one?
Yeah, so when it comes to van der Pol oscillator alone, as I said, this is applicable, this sort of regular perturbation scheme is applicable only when the coefficient is very small. So let's say the coefficient is you have d square u by dt square plus u equals, let's say this is you have a simple harmonic oscillator equation, and with in physical problems you have a very small drag coefficient, let's say in fluids or even for that matter air resistance, which is 0.001 or even smaller, and then you have the damping term given by this, and since epsilon here we can take this to be epsilon, which is a very small parameter, and then we can apply our nonlinear analysis. But if this is very small, even if this is like 0.9 or close to 1, even if it is less than 1, it takes a lot of terms for it to converge. So practically speaking, we won't be able to apply, even if it is not greater than 1 but less than 1, but still of the order of greater than 0.5, 0.6. This sort of method is not practically applicable. So.
Okay, good. Yeah, nice presentation. Yeah, thank you. Okay. I hope all of you have submitted the assignments. Yeah. Okay then. So tomorrow we meet again, and 2 more days to go, isn't it? Tomorrow Thursday, Friday. Friday 4 p.m. we will have the valedictory. Okay. Okay then. Thank you.